Hello, welcome to Lecture 58 in General Chemistry at Andrews University. I'm Dr. Ryan Hayes, and we're going to lead you through electrolysis. It's awesome. It does some pretty amazing things in chemistry and for our world, and we get to learn how and why we use it. And let's get started by a little test question here, a little quiz question. Which of the following is the best reducing agent? Remember, the reducing agent is the thing that gets oxidized with the highest voltage. Pause the video and see if you can guess what it is. All right, let's see if you figured it out. If I'm thinking about reducing agents, I got to think about oxidizing. I got to flip all those chemical reactions around. And that means my only choices are sodium metal, chloride ion, and fluoride ion. I cannot even choose from chlorine, fluorine, and sodium ions. Those are all being reduced, and those are oxidizing agent. So I'm left with sodium and fluoride. And when I reverse that, those reactions, sodium gives me the highest positive voltage. Contact me if you're having troubles figuring that out. All right, so don't forget there's lab materials. You need to go look at that. Normally we'd be running a lab on Monday when we did this talk on electrolysis. Great story here to get it started. Electrolysis has changed our world. In what ways? Let's go back to the story of the Washington Monument. Washington Monument was constructed in the 1780s, and this newly developed material called aluminum that was really awesome and precious, and people were just starting to learn how to work it and make larger things out of this pure metal. So someone decided, hey, since that's such a rare and expensive and valuable material, let's go ahead and craft something that will go at the tip of this really neat obelisk that's in Washington, D.C. Well, there's lots of aluminum oxide around. It's called bauxite all over our planet, but it's hard to get into the pure aluminum form. So somebody figured it out, but it was pretty expensive, about $1 an ounce. And you'd say, that's not very expensive, except that at that time in 1784, that was equivalent to a day's wage. The aluminum apex that was created at the top was about 100 ounces. So 100 days worth of work, yeah, that's quite a bit of money now. And it was the largest cast piece of aluminum at that time. So why do we tell this story? Well, 2 years later, well, here we go. Here's the installation of this aluminum piece. And on sunny days, I've actually seen it glisten. You can see it, a glint, a sparkle of light there at the top. I had a picture of it somewhere. 2 years later, the Hall-Héroult process took aluminum oxide, and used electricity to perform an electrolysis experiment, and they greatly transformed the production of pure aluminum metal. In fact, it became so cheap, it's kind of how we think about it today. And the price dropped, and it's almost worthless. It doesn't take much money now to buy a pretty big chunk of aluminum. There's a link there if you're interested in finding some more details about that. The Hall-Héroult process is just such an important thing in our society and across the world. It uses electricity into this mixture of aluminum oxide using carbon rods here. This is an oversimplification of the process. There's a picture of the red aluminum oxide, bauxite that's being mined. There's some key places around the world where they get it, and then they transform it using electricity. And so it turned this expensive material, using our understanding of electricity and electrolysis, to create a pretty commodity and not too expensive material. About 5% of our electricity in the United States goes to making aluminum. We use it everywhere. It's in planes, it's in trains, it's in cars, it's in pots and pans, it's an aluminum foil that we wrap things. It's all over the place. Pretty strong metal. Doesn't corrode that much, because it has this nice layer of aluminum oxide on it, and you can bend it and form it. There's a lot of things you can do with aluminum. It's great. The process, we make it sound easy, just throw some electricity in it, and you can go look at the commercial electrolytic process to make it, but there's a lot to it. So, but they figured it out, cost came down, and the key part was electrolysis. You see, electrolysis is all about using electricity to make a chemical change, converting electrical energy into chemical products. How do you do that? Well, you use a voltage and power source, something that's creating voltage, like a battery. So you can use a spontaneous chemical reaction, galvanic cell, a voltaic cell, that's what we call these batteries, these spontaneous electrochemical cells. You can use that, the direct voltage there, put it into a chemical mixture, and you can make an electrolysis reaction that will take a reaction that is non-spontaneous and make it happen. This is amazing. Now there's some nomenclature and some symbology that we need to kind of learn about. You see in a battery, the positive terminal was called the cathode. So that's the polarity that was assigned at some point. So how it came about, why it is, we just got to assume that's there. The anode was assigned the negative polarity. We know that as chemists, the electrons flow from the anode to the cathode. Cations in the salt bridge flow to the cathode, and anions flow to the anode. So there's a whole circuit going on. That's taking place there. But in an electrolysis cell, a lot of the same things will take place. At the anode, we're going to drive electrons into that place. Oh, actually, in the anode, the electrons are going to come out. They're going to be like pulled out of that part, and you're going to do oxidation at the anode. So that part's still true. In the cathode part of an electrolysis cell, you're going to do reduction. You're going to push electrons in, and you're going to be able to do some really cool chemistry by pushing electrons in. The only thing that's really changed is this polarity sign. In the anode of an electrolysis cell, it is given the positive sign for the polarity. So the anode actually of the electrolysis cell is hooked up to the cathode. That's why it's a plus plus there. And then the cathode of electrolysis cells is what happens when it's hooked up to the anode of the battery. So you can think of it as like a redox pair that's taking place. The cathode of a battery, that's what's a cathode? Reduction, that's gaining electrons. Where's it gaining from? It's like pulling them from the anode where oxidation is taking place. And then the battery that where there's an anode there, it's hooked up to the cathode electrolysis cell, and you have the push-pull of electrons there. All right, so let's take a look at this electrolysis and how do chemists think about it, and what can we do with that? Well, first of all, we need to understand this term molten, because we're going to look at the electrolysis of molten sodium chloride. What does that mean? What does molten mean? Boiling, rotten, melted, dissolve, a mixture of sodium chloride. What do you think? Well, it turns out molten just means melted. Sodium chloride, it's a salt. It melts at about 800 degrees, maybe 801, somewhere in there, degrees Celsius. If you put in a bunch of heat, you can make it melt. And it'll melt and it'll turn into a liquid. It doesn't turn into liquid water. It turns into a liquid that is nothing but sodium and chloride. Is there any water around? What do you think? Some students, when they've seen molten sodium chloride and go, oh, it's wet. Really? At 800 degrees Celsius, there's going to be water around? No way. 800 degrees, this would have evaporated and long gone. No possibility of water being around. Two metal pieces, so they got to make sure they withstand 800 degrees or higher, so you need some pretty good metals in there. You can drop these electrodes into molten sodium chloride that's been heated to 800 degrees, maybe 850, just to make sure it's all melted. And depending on the surface area, the size of these electrodes at the surface, you can get electrons to transform sodium ions and chloride ions into something else. And all that takes place at the surface, because that's where the electrons take place. That's where the electrons are transferred to the chemicals. What can you do with that? You can do some amazing things. If you can put in the right voltage and the right amount of amps, you can convert sodium chloride into some other materials that we're going to look at in just a second here. So we got to think of the battery pumping in electrons or pulling them out to do oxidation and to do reduction. But it's sodium chloride. Is there any water around? No way. Is there sodium metal around? Nope. Is there chloride ions around? Or chlorine gas around? Nope. Just sodium plus, just chloride minus. So there's only a couple things that can take place when you're in a molten salt situation. Well, here was the question. Were you paying attention? What elements and ions and metals are available to use as reactants when you're dealing with molten sodium chloride? Pause the video, take a look at the options here. So what did you think? Well, the answer is D. There's nothing but sodium and chloride ions. And students all the time are making up things that aren't even there. So this problem actually becomes pretty easy when we're dealing with a molten material because it's so hot, there's no water around, and we don't have to worry about the other pair or the oxidized or reduced material that might be there. That's it, just ions. Don't read into it any more than that. So what can you make? Well, at the anode, you're going to be doing oxidation. The only thing that can be oxidized is the chloride ion. It's the only thing, this negative charge here, that can lose electrons and form anything. So the oxidation potential, go look it up on a potato. You can go look on a table and you can see that's a negative 2.71 volts. That's not spontaneous. But by putting electricity in, you can make this chemical reaction happen and produce chlorine gas. So at the cathode, it's going to take the sodium ion that's there and reduce it into the sodium metal, and the reduction potential is a negative 1.36 volts. Now these redox pairs are going to be partnered together. We add those voltages together, and that gives us a negative 4.07 volts. It's non-spontaneous. That shouldn't happen. But if you are able to put in something more than full volts, yes, like a 9-volt battery, this reaction will take place. Now, it may not go very fast with a 9-volt battery, but it will work. If you exceed that voltage, this chemical reaction will have enough power and voltage potential to take place. So this external energy can be put in to transform these chemical reactions. And what happens? Well, look at what you get for products. You get chlorine gas and you get pure sodium metal. And so this process can be used to create pure sodium metal. How do you get it? Electrolysis. Sodium metal is very reactive, and so you have to store it carefully once you make it. And then if you were to put it in contact with water, it's a good thing there's no water around. It's very explosive with that. Chlorine gas, very reactive, very toxic gas. But this is one way to make it. Here's a little picture showing how one might make it and then separate it. Chlorine as a gas can come ejecting out the top. Liquid metal, sodium metal, can be extracted from the liquid sodium chloride that's there. When you're doing the electrolysis of a molten salt, there's only a cation around and an anion. In this case, it's sodium ions and chloride ions. You can't reduce. Let's see. You can't change sodium. You can only reduce it. You can't oxidize it. Well, why can't you oxidize it? That means it would lose electrons, become sodium plus 2. That is so chemically challenging. Whew, that's not going to happen. So you don't have to worry about sodium plus oxidizing. So the only thing you can do is reduce. And the anion can't be reduced, because if you're gaining electrons, if you're chloride, you'd go to chloride minus 2. That's not feasible. So these are the only two things that can happen in an electrolysis experiment. The cation's reduced, anions oxidized. That's it. Pretty easy to figure out. Now, all of this changes is if you're dealing with an electrolysis of an aqueous solution. The presence of water changes your choices of what can happen at the anode and the cathode. The process of electrolyzing aqueous sodium chloride is actually very important to our society. In 2010, looks like I was going to type in another line there. 2010, 23 billion, that's billion, 10 to the 9th pounds of chlorine and 24 billion pounds of sodium hydroxide are made this way. Where do we get aqueous sodium chloride? Aqueous salt. This is salt water. It's brine. It's all over. In fact, you can drill down in Michigan and get all the salt water you want. Who knew? You can obviously go in the ocean, but there's very concentrated sodium chloride solutions right under my feet right now. Maybe not. Yeah, probably here. All over the Midwest, like Michigan, Ohio, Pennsylvania, parts of Ontario. There's a huge salt layer under there. So much salt, we will never run out. There was huge salt mines underneath Detroit. And they drive trucks down there and just pull out salt and brine and all these things. I even had a cousin that was hauling brine from some wells in mid-Michigan area. Well, what changes when you're in water? So the key word there is aqueous. This changes everything. It's super easy to figure out if you have just the salt in there and what you could electrolyze, but when there's water, some other things change. What changes? Water can be oxidized and water can be reduced. Look at the reaction that could potentially take place at the anode. Two waters get oxidized to oxygen, creating an acid, 4 hydrogens, and some electrons. That's oxidation. it takes a negative 1.23 volts for that to happen. If you exceed that voltage, you might be able to get that to take place. And then water could be reduced to hydrogen gas and 2 hydroxides at the cathode. So I like to remember this, that water gets oxidized to oxygen, or water gets reduced to hydrogen. Okay, so we've got to think about these voltages when we think about what reaction can take place once you're in aqueous solution. Once you know how to write and memorize, I think these are 2 really good half reactions to memorize. Water to oxygen, oxidation, water to hydrogen, and maybe I'll have a little video how you can do this. This is something you can come up with if you couldn't remember or memorize the stoichiometry and the coefficients there. Okay, so now we're going to have to think about which one of these chemical reactions is easier to take place at the anode or cathode. What ends up happening because of the presence of water, it becomes easier to oxidize or reduce water, and it kind of shuts off the possibility of doing things that are higher voltage on both the oxidation and reduction side. And so we're going to see that here in our analysis of the electrolysis of aqueous sodium chloride. So it's not unexpected, but it seems unexpected that we've got to watch out for water. So water is going to compete at each electrode. And so when we think about what can happen at the anode, well, what can happen at the anode? Anode was oxidation. Well, if you have sodium chloride around, you can get the chloride to oxidize at a negative 1.36 volts. But if there's water around, water could also be oxidized at a negative 1.23 volts. So which one's less negative? Which one's going to be easier to take place? Well, it turns out what's easier to take place is water oxidizing to the hydrogen ions to make acid, negative 1.23 volts. So they're pretty close, but this one is more favorable because it has a less negative. We're getting closer to positive numbers because that's where the spontaneity takes over. So water is more easily oxidized than chloride. So at the anode, you'd actually get water, at least it's predicted that water would dominate, and you would just start producing oxygen, not chlorine gas at the anode, okay? So we would favor, oxidation is favored of water, not the chloride. See, that changes. When it was molten chloride to chlorine gas was done, but now we've got something that's a little bit easier to do. It's less negative. We're heading towards positive numbers here. Now we got to go over the cathode and do the same thing. At the cathode, we got to look at the reduction of water versus the reduction of sodium ions into sodium metal. Which one's easier to do? It turns out water has a much less negative, closer to a positive number, and so water gets reduced at the electrode there at the cathode. So everything changes. At least in theory, we'd predict that everything changes when you try to have water in sodium chloride. Water is the only thing because it's easier to oxidize and reduce. So water is the more easily reduced thing than sodium. So remember, you only had sodium ions in there, chloride ions, adding in water. So by checking for water, this is very important. So now those 2 reactions, see, it was a negative 3.94 if you just had, or somewhere around there, if you had just sodium chloride. But now if you had water, their 2 half reactions add up to a negative 2.06 volts. So once you put in anything over 2.6 volts, 2.06 volts, then that reaction takes place. So in theory, we would predict that water, and this is what my general chemistry students need to think through, when there's water in there, you've got to compare the half reactions with water. The lowest negative number is the one that will work. Now, interestingly enough, the reality is that there are some kinetic things that you don't need to know about at this point. And because the potentials at the anode are pretty close to each other, turns out chloride does end up winning out here, okay? You don't need to know this, but I mean, it's actually important to know this because chloride does get made to chlorine in reality. So this is why in our society, chemists or chemical companies actually can use electrolysis, and chlorine gas is made at one of the electrodes. But sodium hydroxide is made at the other one because of the oxidation or the reduction of water into hydrogen gas and sodium hydroxide or hydroxide. Okay, so we gotta keep that in mind when you're dealing with an anode. So this is actually what ends up happening there. So if you have well, this is another example. So if you have water around with a salt, you got to compare that. So here's the chlorine. So you're going to wonder, what am I supposed to pick? You just said in reality that's the one that picks. All right, but let's take copper chloride, another example here. So overall, copper and chloride, copper would be reduced, it's the cation, chlorine would be oxidized, and you can see the voltages there. And it's actually really easy to reduce copper. And overall, this is a negative 1.02 volts. You just got to put in about a volt, and this would take place. Except if you're in water, you need to think through what might take place. And I think you'll find, if we were to go study this one, that water would beat out chloride, again, same thing, but the copper ions, actually because of their reduction potential being positive, will definitely beat out water. So the copper reaction would still take place. So this is what I would get for the preferred electrolysis reaction. In theory, based on the voltages, water would be oxidized instead of the chloride, and copper, because of its lower, in fact, more positive voltage than water's reduction, would take place. The overall E cell negative 0.089. So that is a lower overall E cell, and that's how we would figure out what would take place at the anode and cathode. So that's part of your job, is to figure out how to do that. So what do we learn? Put in electricity. You can make non-spontaneous reactions happen. That's what makes our metals. We get some very important chemicals like chlorine. Go look at what chlorine is used for. So many things. Sodium hydroxide. So many things that chemists use bases, strong base like sodium hydroxide. So electrolysis is the way. And it's a very powerful chemical tool for our society. Hope you learned a few things here about chemistry, electrolysis, and its impact on our society. And go review those steps between molten and aqueous salt electrolysis. There's a lot to learn there and to digest. And so we'll see you in the next video.